All right, so section 2.4, which is the last section we're going to cover in chapter 2, talks about solving recurrence relations. So solving a recurrence relation is converting a recursive definition to a closed formula, okay? So recall that a recurrence relation is a recursive definition with initial conditions. It probably has a sub 0 or a sub 1 defined. So here we have a recurrence relation. I want to solve it. So I want to determine its closed formula. So why don't we go ahead and try and do that? So I know a sub 0 and a sub 1, right? This is going to go as a sequence, so I should probably find a couple more terms. So let's look at a sub 2. A sub 2 equals 5 times a sub 2 minus 1 minus 6 times a sub 2 minus 2. So I have 5 times a sub 1 minus 6 times a sub 0. And you don't have to write out all these steps. It's just what I like to do when we're first getting started. That gives me 5 times 2 minus 6 times 1. 5 times 2 is 10. 6 times 1 is 6. So I get 4. So now I have my series. Let's write it up here. 1, 2, 4. Okay, let's figure out another one. If I have a sub 3, that's 5 times a sub 2 minus 6 times a sub 1, which is 5 times 4, what we found before, minus 6 times 2 is 20 minus 12, which is 8. Can you see what sequence we have going on here? Let's find one more term just to be sure. A sub 4 is 5 times 8 minus 6 times 4. That's going to give me 40 minus 24, which is 16. So I'm sure we can guess what this sequence is. So here I have a sub n is 2 to the n, right? Because 2 to the 0 is 1. So we get a sub 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8, and so on. So there we solved for this reoccurrence relation. Let's try another example. Here I have a sub n. It equals 5 times a sub n minus 1 minus 6 times a sub n minus 2. And we have our initial conditions, right? A sub 0 equals 2 and a1 equals 5. So let's find a sub 2. A sub 2 is going to be 5 times 5 minus 6 times 2. And that gives me 13. So we've got 2, 5, 13. Okay, I've got a sub 3 equals 5 times 13 minus 6 times 5, which gives me 35. And a sub 4 equals 5 times 35 minus 6 times 13, which is 175 minus 78, so I have 97. 13, 35, 97. Are we seeing any kind of pattern here? No. No, we're not. Okay? Well, okay, so we've learned some stuff in the previous section, right? If we look for the continuous sum of differences, right, we can figure out what degree this polynomial is going to be. So I could look for the difference. So the difference between these two is 3. Between these two is 8. Between the next two is 22. Between the next two is 62. Okay, let's try this again. 5, 14, difference of 40. It doesn't appear that these, 9, are going to have the same difference. So what do I do now? I haven't learned how to approach these problems. Well, that's what we're going to learn in this chapter, especially towards the very end of this chapter. Friendly reminder to check your answers. And one thing you can do is you can always check that a closed formula is a solution to a reoccurrence relation using substitution. We love substitution in math. That's why we teach it early on in algebra. So why don't we check that a sub n equals u to the n plus 1 equals a sub n, which equals a sub n minus 1 minus 1. Okay, so how am I going to do that? I'm going to substitute this in for this. So I have a sub n is 2, a sub n minus 1 minus 1. Now I have a sub n equals 2 times 2 to the n minus 1 plus 1, right? Because I got to substitute in for a to the n minus 1 minus 1. So let's go ahead and distribute that 2. That gives me a sub n, which is 2 times 2 to the n minus 1 plus 2 minus 1. Now here, I know I have 2 to the first. And when we're multiplying exponents together, we add those exponents. So this is really 2 to the n minus 1 plus 1, which gives me 2 to the n. I combine like terms, plus 1. So we can see that this is indeed the solution for our recurrence relation. Let's talk about telescoping. So telescoping refers to the phenomenon when many large terms cancel out, so the term telescopes. What does that mean? It collapses. Telescopes used to, look kind of like this. Oh, I'm a terrible artist. I'm sorry. And you could collapse them down really tiny so they'd like fit in your pocket, like a tiny little telescope. So that's where the term telescoping comes from. So why don't we go ahead and solve this using our approach to telescopes. So let's go ahead and find the first few terms. So a sub 0 is 4. A sub 1 is 4 plus 1, right? Because our term is the term before it plus n, so that gives me 5. A sub 2 is 5 plus 2, which is 7. A sub 3 is 7 plus 3, which is 10. A sub 4 is 10 plus 4, which is 14. I could do this all day, guys. A sub 5 is 14 plus 5, which is 19. Okay. I'm not seeing any pattern, right? I mean, the difference here is 2, 1, 3. It's increasing by n each time. So this is not super helpful, okay? Unless I rewrite this another way. So the difference each time, the difference between each term is n. So if I have a sub n minus a sub n minus 1, the difference is going to be n. So let's go ahead and write this out. I have a sub 1 minus a sub 0 is 1. A sub 2 minus a sub 1 is 2. A sub 3 minus a sub 2 is 3. A sub 3 minus a sub 4 minus a sub 2 is 4. And this goes on and on. So what do I have here? I have on this left side, if I was to take the sum of all of these, let's change colors so we can see what's going on, because we're going to get real tricky. So what we're going to do is we're going to take the sum of our left side and the sum of our right side. So over here, what you can see is I've got my a sub 1s are going to cancel out, a sub 2 because I've got a2 minus a sub 2, a sub 3, all the way, everything's canceling out except a negative a naught and an a sub n. So on the left side, I'm going to have negative a naught plus a sub n. Well, what do I know about this right side? Well, this is the sum of all numbers. And we learned in the chapter on sequences and series how to write this series as a sum, and that's going to be n times n plus 1 divided by 2. So now we have our left side and we have our right side. Okay, I want to solve this for a sub n. So if I add a sub 0 to both sides, I have a sub n is n times n plus 1 divided by 2. And what's a sub naught? 4. So this is my final answer. I have written this telescoping recurrence relation in closed form. This here is the closed form. There is another way to solve this problem, and that's using iteration. So why don't I write that out for you, us? So I have my relation and my initial condition. I now know that, let's use orange, a sub 1 equals a sub 0 plus 1. A sub 2 equals a sub 0 plus 1 plus 2. A sub 3 equals, stick with me, a sub 0 plus 1 plus 2 plus 3. And this goes on and on until a sub n. That gives me a sub 0 plus 1 plus 2 plus 3 plus ... plus n minus 1 plus n. So I have a sub n is a sub 0 plus 1 all the way to n. And we know how to write this as a sum. So that means I have a sub n equals 4 plus n times n plus 1. Sorry, it's minus 1, isn't it? Minus 1 over 2. So the same thing would have been true for the previous slide, that this should have been a minus 1. My mistake. But that's how to solve it through iteration. Isn't that exciting? Let's do one more iterative example. So I have a sub 0 is 1, a sub 1 is 3 times a sub 0 plus 2. A sub 2 is 3 times 3 a sub 0 plus 2 plus 2. And I know my parentheses aren't quite right here, guys, but I'm trying. Next, I have a sub 3 equals 3 times 3 squared, a sub 0 plus 2 times 3, right, because we got to distribute that 2, plus 2. And a sub 3, if we resimplify that, that's going to give me 3 cubed a naught plus 2 times 3 squared plus 2 times 3 plus 2. So I can go ahead and rewrite this for a sub n. That's going to be 3 to the n a sub 0 plus 2 times 3 to the n minus 1 plus 2 to the 3n minus 2 plus ... all the way to 2 times 3 plus 2. So I can go ahead and simplify all of this, right, by combining like terms to 2 minus 2 times 3 to the n. You can't see it now. This simplifies to 2 minus 2 times 3 to the n over 2, which simplifies to 3 to the n minus 1. So a sub n is 2 times 3 to the n minus 1.